Welcome back to College Algebra. In this lecture video, let's continue with our objective number 3. All right, finding the zeros. Oh, sorry, it was right here. Finding the zeros of polynomial function by applying conjugate roots theorem and our rational zero theorem. So these type of problem want us to, again, finding all the zeros of polynomial, but we need to make sure to find the appropriate number of solutions counting the multiplicities. Okay, so we're gonna really kind of think about this a little bit. All right, so let's do the same way as we done in previously. To find the zeros, just straight up from the polynomial function, we got to do our p over q. So since my q is 1 up front, so all my potential rational zeros will all be whole numbers. So I'm just going to go ahead and graph it and see what's going on with my graph. Minus 13x squared. All right. So I need to think about the multiplicity now, because before, back in section 4.3 videos, all we did was basically assuming the multiplicity is 1. But now I really got to think about it, since the problem even says counting the multiplicity. All right, that's a cross right there. So if I go look on the table, that will be 3, 0. Okay, so it crossed. So the multiplicity is odd. But now I have a decision to make. Degree is 3. So is this odd, 1 or 3? Is this the only zero I have with a multiplicity of 3 or 1? So to determine that, I would need to use my zero to knock my exponent down to a quadratic. Okay. And then from the quadratic perspective, then I can decide, okay, whether my multiplicity is 1 or 3. Because if it's a 1, then the other two zeros got to be non-real zeros. Okay? If I don't have any non-real zeros, that means the zero, my 0, 3 is actually 3 of the same numbers. That's how we can get x minus 3 to the third power. But right now, I don't know if it's 3 of the same zero or just one of these 3, and the other two are non-real. So I don't know that until I actually check it out, the synthetic division. So let's go ahead and do that real quick. 1, negative 13, 56, negative 78. No missing terms. So let's go ahead. 3 times 1 is 3. Add them up is negative 10. That's negative 30. That's 26. 3 times 6 is 18, excuse me, carry 1. 3 times 2 plus 1 is positive 78. So my remainder is 0. So now looking at this leading coefficient 1, that 1 means 1x to the second power. So minus 10x plus 26 equal to 0. All right, so this is not factorable because 26 is probably 2 and 13, and 2 and 13 can never give me 10 in the middle. So now I got to use my quadratic formula. All right, negative b is negative 10, right? Plus minus square root of my b, negative 10, whole thing squared. Minus 4 times my a is 1, c is 26, whole thing over 2 times my a, which is 1. So when we reviewed the quadratic before, we always put what's inside the square root into the calculator and see what the number come out to be. So that's negative 10 squared minus 4 times 1 times 26. All right, so that's negative 4. Ooh, that's not too bad. So this is going to be x. This is going to be x equal. Negative 1 times negative 10 is positive 10 plus minus square root of negative 4, whole thing over 2. So square root of negative 4 is the same as 2i. So this is 10 plus minus 2i over 2. So when all three numbers on the outside can be reduced, we'll reduce them. So that will be, if I reduce them all by 2, then that will be 5 plus minus I, right? you don't have to write 1 before the I, and you don't have to write 1 in the bottom. You can just say 5 plus minus 2I. All right, so my zeros are x equal to 3. The other two is 5 minus I and 5 plus I. So with the other two non-real zeros, okay, that means my multiplicity on my 3 got to be 1, because 1, 1, and 1 all going to add up to be third power. And it kind of makes sense, right? Because remember now, if I were rewrite my 3, 0 back into factor form, what should I write on top of what exponent should I have to write on top? I got to write 1 for each one of these in order to add up to 3. Okay, so I know these are my answers. All right, let's look at a different one. All right, so this one is a little bit big. 5 power. So let's real quick do my rational zero theorem, P over Q. Q is 1, so I'm not going to have any potential fraction zeros. So we can go straight to the graphing calculator and graph this function. And let's see what's going on here, okay? To the 4th plus 24x to the 3rd plus 24x squared minus 25x minus 25. All right. 5 power. Ooh, what's going on here? What's going on right here? All right, let's look. Negative 1 and 1 so far. So apparently, at 1, it crossed it. But what's going on at negative 1 right here? It looked like a negative, well, it is a negative 1 because I just saw on the table. Cross at 1. So let me investigate, okay? So to cover negative 1, to show up, to have negative 1 showing in the middle, I'm going to just go from negative 2 to 0 on my window. I got to make sure that it's either a turn or a cross. It's too small for my eye to see. Okay, all right, nothing juts out above the x-axis, so that's a turn. All right, degree is 5. Turn means even power. Cross means odd power. So what kind of even power, what kind of odd power can I use? Can I do a 3 and a 2? Sure, that adds up to be 5. But how do I know for sure? Okay, what can it be? 2 and the 1, but that will only add up to be 3. So that make me have 2 missing ones. Okay, 2 missing zeros. So to determine what multiplicity, okay, is on the factor of my 2 zeros so far, I have to what? I have to knock this exponent x to the 5th power down to a quadratic and see what kind of zeros I may have for my quadratic. So if my quadratic is going to continue to give me negative 1 and 1, okay, then I would know exactly what my multiplicity is. All right, so let's write this out, okay? Let's write this out. 1, 1, 24, 24, negative 25, negative 25. Oh, hold on a minute now. Okay, even, smallest even is a 2. So if I assume at negative 1, the multiplicity is 2, that means I have 2 of these negative 1 I can use. And if I assume the cross is a 1, that means I can use the 1 time, but I can use negative 1 twice if I'm assuming it's only multiplicity 2. Now I could have used it 4 different times, but I don't need to use 4 times. To knock 5th power down to a quadratic, I just need to do synthetic division 3 times. So I'm going to use 1 time and use a negative 1 twice for the multiplicity. So I'm going to use negative 1 start out with. and not these exponent down. So bring down the 1, that's -1, that's a 0, that's a 0, 24, -24, that's a 0, that's a 0, that's a -25, and that's a positive 25. All right, so that remainder 0. So now the leading term is 1x to the 4th power. So I'm going to use -1 one time, okay? Bring it down. I'm assuming there's 2 of those -1. I'm assuming the multiplicity is 2. So that means I got 2 of the same 0. -1 times 1 is -1, add them up. That's positive 1, that's 25. That's -25. Add them up is -25. Multiplying is positive 25, so that's a 0. Okay, so that's my remainder. So this is going to be 1x to the 4th power now. Third power. So now I used up the 2 -1. I'm assuming for the multiplicity. So I'm going to just use the 1 time. Then I get my quadratic. 1. All right. 1 times 1 is 1. Add them up 0. This is 0. That's 25. 1 times 25 is 25. Add them up 0. Voila. So now this leading coefficient 1 is 1x squared plus 0x plus 25 equal to 0. So this is not going to give me 1 or -1 for my other zeros. So my assumption was actually correct from the beginning. This is going to be x squared equal to -25. So when I take the square roots on both sides, my answer will be x equal to positive and -5i. So that means, back up to the top, that means the other two zeros were non-real zeros. So they come in conjugated pairs. So we can say those multiplicity is 1 and 1. So my assumption of -1 has multiplicity 2 is correct. So the crossing one is 1. So now I can add up to be 5 power. All right. Is that always the case? It all depends. The graph and what happens when we broke it down to a quadratic. Okay, it really depends. All right, let's try one more, okay? All right, let's try this one. This one is a little bit, doesn't look kind of ugly. But if I do my P over Q, I'm still good. Q is 1, so all my potential rational zero is going to be integers. So I'm just going to go ahead and graph. Hang on one second. All right, let's type x to the 5th plus 5x to the 4th. Plus 11x to the 3rd plus 23x squared plus 28x plus 12. All right, so real fast. One, that look like a turn right there. By the leading term test, once that thing goes up, it probably never come back down again because I power, remember I power leading term test, right side goes up, left side goes down. So, that look like a turn. I need to make sure that's a turn, okay? So let's find my zeros real quick. I got -3 and -1 so far. All right. So let me make sure that's a turn, because sometimes it may look like a turn, but you actually cross it and cross it back. And that matters, because if it cross it and cross right back, that means I got another 0. But I don't think it will be that case here, because I don't see another one near it. But I'm just going to double check. That's -1 there. So I'm going to do it from -2 to 0 again in my window. So I can take a closer look. See how it flattens before it kind of curve. So that is a turn. You never went below it. I think on the homework there might be questions where there might be a problem where you actually cross right back. So watch out for those, okay? All right, so turn at -1, cross at -3. So that's the same thing as what we did earlier with the previous problem. Do I automatically assume is it going to be cross at even multiplicity 2 turn at 1. And maybe I got two other non-real zeros, or maybe this is 4 and that's a 1. Okay. Or maybe a 3 and a 2. Right? Cross is even, turn is odd. So I don't know. I'm just going to go ahead and do my synthetic division and see what my quadratic equation reveals. So if I'm assuming, oh Lord, got the number backwards. Cross is 1, turn is 2. So if I'm assuming the turning at -1 is 2 of them, multiplicity, that means I can use -1 twice. I can use -3 one time. So let's write this out. 1, 5, 11, 23, 28, 12. All right, let's see what we got. I'm going to start with -1 twice, okay? So bring down the 1. That will be -1. That's a 4. This is a -4. 11 plus -4, -7. That's a +7. That's 30. -30. -2. Oh, I messed up somewhere. 1, 5, 11, 23, 28, 12. Did I mess up somewhere? Oh, crap. That is a +7. Duh. Did it too quick. All right. 11 plus -4 is +7. -1 times 7 is -7. All right. 23 plus -7. 23 plus -7. I'll give you 16. There you go. So that's -16. 28 plus -16 is supposed to be 12. All right. -1 times 12 is -12. My remainder is 0. All right. So this is 1x to the 4th power. Let's continue couple more times. Using -1 again. Bring down the 1. There's -1. That's a 3. That's -3. That's a 4. That's a -4. And that will be a +12. So -1 times 12 is -12. Remainder is 0. So this is 1x to the 3rd power now. All right. So now using -3 to get down to quadratic. So put on the 1, that's -3, 0. That's a 0, that's a 4, that's a -12. Voila. So this is 1x squared plus 0x plus 4 equal to 0. So the other two zeros are imaginary. So bring this over. So that gives me x squared equal to -4. Take a square root on both sides. The other two zero, x equals positive -2i. All right. So that's the other two zeros. So the multiplicity on the two non-real zero got to be odd, 1 and 1, because 1 and 1 add on my 2 when they turn, and the 1 when they cross, give me the multiplicity 5. All right. So, basically, this third objective, we just used rational zero theorem, we used conjugated theorem, conjugated root theorem, and synthetic division to help us to find all the zeros. Okay, counting the even and odd multiplicity. All right, that will conclude this lecture video. Thank you for watching.